So welcome Alan, G4FZP, to the Berry Radio Society with Warrington Amateur Radio Club talk on building a power supply from junk. Over to you, Alan.
Okay, welcome everybody. I'm conscious that I've probably got a lot of people on here that are far more expert in switch mode power supplies than I am, and also that we've got an international audience. So obviously I'm in the UK. Please try and translate what I'm going to give you and turn it into American or whatever nationality mains it is that powers your shack. Things may be slightly different where you come from, but we'll try and accommodate it and not get anybody fried. This project that I'm going to talk to you about this evening kind of started when I got back into the hobby just after my retirement, which I was fortunate to do after a very long working career. Background, I started off as a BBC transmitter engineer, did that for a while, got into technical authorship, and then defected from there into IT, specifically networking. But my whole life really I've been tinkering about with things, breaking things, repairing things, fixing things and building things. So once I got back into the hobby, one of the things that I realized pretty quickly was that I needed a 13.8 volt power supply, and I didn't have one. My daughter bought me a little Baofeng handheld. I quickly bought myself a little 2-meter rig, Retrevis thing it is. You'll see it later. And of course, nothing to plug it into. So I got to thinking, well, what can I do here? How can I fix this? I need a 13.8 volt power supply. And the other disclaimer I've got to give you is, as Tristan well knows, I'm a Yorkshireman by birth. For those of you in foreign climates who don't know the kind of intricacies of UK society, Yorkshiremen have a reputation for being very tight with their money. We don't like to spend anything if we can possibly avoid it. We like to get everything for free if possible. And so that's where this began. So I began to have a look around on eBay, see what I could find, and here's just one that I picked out of the many just to show you. I haven't seen anything half decent for under £30. Most of them seem to be a bit more. That one there that you're looking at looks rather suspiciously to me like the form factor of an ATX power supply with a nice front panel on it and a coat of grey paint. Let's pay £66 for it. A Yorkshireman is a Scot robbed of his generosity. Well, I'm not going to say anything because it may upset the Scots. But yeah, we do have a reputation in Yorkshire for being thrifty. Let's just leave it there. So I didn't want to pay 66 or £80. I was just picking up the hobby. I wanted to do something for free. I began to have a look around to see what I've got kind of floating around in the shack here. And I'll show you the state of the shack later. One of the things that I've been doing is I had a number of old PCs that were of no use whatsoever.
Still a picture of me,
different ones that have
there's picture in it.
Hello, somebody's unmuted there. I don't know what it is. Show us a picture of it, somebody said. I will in a minute. At the end, I began to have a look around in the shack, and as I said, found some old PCs, dug the power supply out, and I thought, well, how about making one for free? Convert an old ATX power supply. There's one that I have in my cupboard. It's not the actual one that I built. I'll show you one later, but this is one that is fairly typical. I just ripped that out of an old PC that I've got the remains of down on the floor, actually. Take a closer look at what these supplies can do by having a look at the label on it. And you see something like this. There's a lag on my phone, so I hope the pictures are keeping up with what you're seeing on yours. This one claims to be easy cool, 600 watts. And very helpfully, it's got the wire color codes at the bottom there, along with the outputs that it alleges to be able to do. And you can get 12 volts at 18 amps out of this thing. Well, that's very nice. I could just run the rig on that, but I thought, come on, let's try and get this to 13.8 and squeeze a little bit extra out of the finals. And you might also notice on there that it claims to be like, you know, it has short circuit protection, it has various other things in it, and quite a useful little unit, to be honest. So move along a little further. I'm juggling papers and stuff. This is the one where people would probably contradict me and know much more about switch mode power supplies than I do. But I'm going to give you the FZP level overview of what we're dealing with here when we deal with one of these boxes. If you look on the top left corner, really, you've got the incoming AC supply, which we want to convert into some nice DC voltages. And you might think, well, this system here in front of me has been designed by an absolute maniac, because like the first thing that we're going to do is stick the incoming AC supply straight into a bridge rectifier. Now, let's not stand on ceremony. Let's just rectify the mains. Why not, you know, get straight in at the deep end. And then we're going to filter it. We're going to stick some big electrolytic capacitors on it and some chokes and turn it into basically very high voltage DC straight off the mains. And then now we've got some DC. Now we're not going to settle for that. We're going to chop the DC back up again and turn it back into AC again, which we had in the first place, but never mind. We're going to drive a high frequency switch, a pair of FETs or transistors, usually FETs, to generate a very high voltage AC, which we will then stick through a step down transformer to produce low voltage AC. We'll rectify that again, filter it, and then we'll get some output. And how the thing regulates basically is it takes the output, feeds it back into a comparator, which you'll see down at the bottom of the screen there. There's an error detector. It's basically an op amp inside of, usually this is all done in a driver IC. And the error signal coming out alters the pulse width modulation of the signal that's driving the switching FETs. There's some kind of isolation in there to keep the mains away from the back end. This diagram shows an opto-isolator. Sometimes it's through the transformer itself, but that's basically how it works. Crazy. So on the one printed circuit board that you've got inside your unit there, you've got chopped up mains, you've got high voltage rectified mains, you've got high frequency, high voltage, you've got all kinds of insane things. So before we move in any further, I want to give you a little bit of safety information. I've got at the top there, switch mode power supplies are dangerous and can kill you. Well, yes, it's true. When I talk about danger, I'm not saying this is so dangerous you should never touch it. A ladder is a dangerous thing. If you don't work with a ladder correctly, you can suffer serious injury. Well, a switch mode power supply is the same thing, really. It's not a piece of nuclear waste. It's just something that you have to approach with the right kind of mentality if you're going to work on this thing. And that's why it's important just to run through these little points here that I've picked up and things that some people may not know. First thing to remember is that this power supply is not isolated from the mains. What I mean by that is that the output side, where the 12 volts DC comes out, the negative side of that is probably going to be, you know, isolated. It's going to be connected to the case, which in the UK certainly will be connected to mains earth or ground. That's okay. But the other side of it, where the mains comes in and is rectified, the negative side of those capacitors there is not going to be referenced to mains earth or ground. It's going to be referenced to mains neutral. Where this comes in is if you decide that you're going to take your scope and have a look at, for interest's sake, at the switching waveform or something, your scope is probably fitted in the UK with a 3-pin plug, and I bet it has a metal chassis. All the old ones certainly do. Mine does. So when you touch the negative side of your scope probe and try and clip it on somewhere to get a measurement, you're making a bridge between mains neutral and mains earth. That's not going to do your scope much good, and it may not do you much good. So the safest thing to do is to assume that everything inside of that little box is live at mains voltage. That's what I do. Even the 12 volt output, I won't touch it. When it's on, I just treat the whole thing as if it's live at mains. And if you do that, you won't go far wrong. Also worth pointing out that those input side DC caps, where we rectify the mains and then smooth it, They can hold a charge. You can have over 300 volts DC on there, even when the thing is turned off, and that can give you a nasty belt. So please be careful. Yes, in any normal state of the world, there should be bleeder resistors on there. But remember, these things are designed, they're a commodity item. They're designed and churned out by the tens of thousands in some little Chinese factory where every penny counts. They may not have fitted those bleeder resistors. You don't want to depend on them being there. Just assume those caps are charged and don't touch anything. The heat sinks inside of the case may be live. Yes, if we were building it, we'd put in a little mica washer and we'd put in an insulating kit. But hey, you know, pennies count when they're building these things. And if it's inside a nice case and nobody's ever going to touch it, are they? I wouldn't like to trust my life to that mica washer being there. So assume the heat sink's alive too. I found one that actually was. So there you go. My watchwords for doing it: always unplug the mains lead and let it sit for a short while every single time before you take the board out or before you do any work on the board. Don't do it with it plugged in. My personal approach is I never run it with the board out of the case on the bench. I'll do what I'm doing. I'll put the board back in, secure it with at least 2 screws, and then test it that way because it's just safer. Another little pointer is if you want to measure something when it's on, the best way to do it is to solder a little jumper wire onto there, bring that out of the case, attach your meter to it, and then you can turn it on without having to probe around inside and risk slipping with your probe and going somewhere where you should go, where you shouldn't go, should I say. The old adage, only work on it with one hand at a time. And if you stick to a battery powered, you know, normal sort of hands-free multimeter that you'd use on your bench, you'll be okay. I wouldn't use anything more than that to work on these. If you find yourself needing anything more complicated than that, why are you bothering? It's a power supply for free from junk. If you've got such issues with the power supply that you happen to have got that you need more than basically a digital multimeter that runs off a 9-volt battery, throw it in the bin and get another one. It's not worth it. Life is too short, and you could make yours even shorter. So there you go. There's the safety briefing over. Let's move on a little bit. Some caveats to pick up some questions that I'll probably be asked at the end if I don't cover them now. Yes, these things switch at between 20 and 30 kilohertz. The one that I built is as silent as the grave. I have it virtually on top of my HF transceiver here, and you can't hear a dicky bird coming out of it. I have another one that I built into a bench power supply that is absolutely hideous. I need to take it apart sometime and fix that. And that basically generates sproggies every 35 kilohertz all the way up the HF bands, all the way from 80 meters up to 10. So, you know, your mileage may vary. If the unit comes with a decent input mains filter in it, or you're prepared to add one, and it's got some decent output filtering, you'd probably be okay. But again, you know, if you're really struggling with this, just bin it and get a better one. You can find these everywhere. The other thing to remember is you'll be pushing the component tolerances. On mine, the smoothing caps on the 12-volt rail are 16-volt electrolytics, and I'm taking them up to nearly 14 volts. So you are pushing it a little bit, but as long as you're sensible, you'll be fine. And if it worries you, you could always replace them with higher voltage ones. Another thing is that quite often when you get these out of an old computer, you'd run it on the bench and you found out that the fan is a hideously noisy groaning thing. Well, again, you can swap the fan or just get another one. But things to bear in mind there. Benefits of doing it, well, it's free, or at least extremely cheap. And you'll get all the built-in ATX power supply features. You get power factor correction, so it's not a horrible load. You get under voltage and over voltage protection that shuts the supply down, short circuit protection, and usually some kind of overload protection and thermal shutdown as well. So these are things that are worth having. Okay, let's move on a little bit then. Having got your power supply out of some old computer, we're going to move into now how to actually work on it. Hope you're going to be able to follow this okay. You want to test it first of all. Stick it on the mains, obviously, put some mains into it and give it a try. But one thing you'll find is that out of the PC itself, these supplies don't do anything. because they're relying on a circuit coming back from the innards of the computer to tell it to turn on. So find the big plug, which you've got a picture of there, the one that goes into the motherboard with all the wires on it. Identify the green wire, which the non-color challenged of you will be able to see there right in the middle of the picture. Just use any old bit of wire that you've got and just short the green one to any of the blacks. That'll make it start up. And that's what you need to do at the end. When you've built this thing, you want to connect the green to black permanently, and it'll come on all the time. Having got it to start up by shorting the green to the black, you can go through and you can measure those output voltages and see if your supply is working. The yellow wires should give you something around 12 volts, probably 11.6, I would guess you might get. That doesn't mean the supply's bad. It just means that it's not regulating on the 12 volt rail, which many of these old ones don't. But don't worry, we're going to fix that. Red should give you a nice 5 volt supply, and orange should give you 3.3. You can take it as it is, and you can make a nice multi-voltage bench power supply out of it. As I said, with the caveat that it doesn't regulate very well on 12 volts, but there's a video I just watched the other night on YouTube that Stephen sent me. A guy builds one, and his trick is he just loads the 5 volt rail a little bit with a fat resistor, and that makes it regulate. It's not perfect, but hey, if you just want it for testing things and playing about on your bench with electronics, why not? There's something else you can do with an ATX power supply. But we're going to turn it into something for our rig. Take the lid off. That's a particularly hideous example of what they look like inside when you take the lid off. I didn't clean it just for the picture. That is just as mine looked when I first took the lid off it and took this photograph. First thing I would do is check the capacitors. If they've got bloated ends, throw it away. Not worth the effort. If the caps look good, well, you can carry on. You've already tested it, you know it's working. Your capacitors look good, there's nothing horrible on the board, so it's probably going to be a goer for your conversion project. If you can remember back to the diagram that we saw, we can identify some of the things inside this supply here already. There's the mains input at the top, and you can see that this particular one has got the big yellow capacitor there, and underneath that you can't see it very well, but there's a nice toroid filter. So this one's got a little mains filter daughter board in there, so this is probably going to be a good one to use. Over here, there's the two big electrolytics smoothing the rectified mains. The rectifiers for the mains will be on the heatsink just to the left of those caps there, the high voltage side of the heatsink. The big thing at the bottom there is the power factor correction choke, which is just used to make it give a better load on the mains. That's not the transformer. The transformer is here, forming the bridge in this case between the deadly mains side and the more benign DC side of the operation. So that transformer looks very small for the output it's been given, but that's because it's running at 20 to 30 kilohertz. That's one of the reasons why they do this. You can make the ironmongery much smaller, you can get much higher efficiency, and you get better control. So that's why they do this. The other side here, this is the DC side, various smoothing capacitors for the various different outputs, and a bit of filtering there you can see on the toroids that are wound round on the DC outputs. So that's roughly what's in there. Here's a little bit of a better view of the inside of it, and what you want to do if you're going to convert one of these supplies is you want to try and find the control IC. As I said, all the pulse width modulation stuff and the drive for the switching FETs is usually done on a single chip. If you have a look at your power supply when you've took it apart, you're looking for the biggest chip, and it'll be somewhere on the DC side, most probably. Occasionally, you do get another daughter board on the mains side, and they roll the driver chip into active power factor correction. I haven't even bothered with that. If I got one of those, I'd just throw it aside and say, no, I'm not doing that. It's too complex. But you do come across those sometimes. On this one, the chip is there. You can see it's the biggest chip on the board. There's another little op amp just below it, but that's the one. Identify it. Have a good look. Get your magnifying glass. Find out what the number is on there. This one happens to be a 2005B. And this is where the magic happens. Google is your friend. Get on Google and look for the data sheet and application notes. Somebody told me you're always struggling with these because you can never, ever, ever find a circuit diagram or a schematic for these things because they're just built in these, you know, little factories somewhere. But what you can find is the data sheet and the application notes for the control IC. And you'll find 9 times out of 10, if you look that up and find those sheets, especially if it gives you application notes, it gives you a sample circuit or maybe 2 sample circuits. And I'll bet a bottom dollar that the circuit diagram of the board that you're looking at is almost identical to that, because these designers don't like to do any work. If they can just use the application note sheet to build their power supply, they will. At the bottom of the screen there is some ones that I've come across. You may find some of them, you may not. If you find something that's really obscure and you can't find any sheets or any information for it for love nor money, again, just use it as a bench supply, don't worry, because you do need to find the information, and I'll show you why. So we've identified what control IC we've actually got in there. Now we're going to go ahead and we're going to, he says, trying to turn over his paper. There we go. Now we're going to have a closer look at that. So here's the chip, and there's pin 1. If we look at the data sheet, which I'm going to show you very shortly, for this particular IC, the control input where the magic happens is pin 1 on this particular chip, and there's pin 1. So what we're going to do is, starting at pin 1, I'm going to trace the circuit board basically and find the components that are connected to pin 1, because we're going to need those later. So on my particular supply, it's this resistor here is involved in it. This resistor here is involved in it, and one of these up here is connected to it. You can do this in all the time-honored manner, you know, take the board out, shine a light against it, follow it through, use your multimeter, look out for links and jumpers and things like that, and make sure you've traced out exactly what that circuit is that's connected to the pin that's of interest. Why am I telling you this? Let's look at the circuit from the application sheet and you'll see why. Here we go. This is just pruned straight off the application notes for that particular chip, the 2005B even. The way it works is, if you remember back to the switch mode power supply block diagram, we said that there was a comparator. You can see that there in the bottom of the IC. Pins 1 and 2 of the IC are connecting to the input, and pin 3 there also is driving into the PWM at the top of the diagram. So you can see the comparator down there, and you can see the resistors that are attached to it. This particular one, you have to provide an external reference, and there's the external reference here. R5 and R4 just making basically a potential divider across the 5-volt rail and giving you some voltage which is being fed into pin 2 of the chip. Usually you'll find that's 2.5 volts. Occasionally the designer might have had a brainstorm and decided to use 5 volts, but normally R5 and R4 are equal values and you have 2.5 volts there. That's your reference. And so the way it works is, you'll see on pin 1 another pair of potential dividers there coming from the 12-volt and the 5-volt rail, and this is the sensing. So basically that comparator in the IC is just comparing what comes in from on pin 1 with what's coming in on pin 2, sorry. I'm going to try and get this right. And it's comparing the two. So as the output voltage changes, it will either increase or decrease the pulse width, and it will change the drive to the transistors, and so it's regulating. So all we have to do is change that regulation there in the green box that you're looking at, so that instead of 12 volts coming in, we have 13.8 volts coming in, giving us the correct voltage at pin 1. Because if the supply's happy, if the outputs are exactly where they need to be, pin 1 will be equal to pin 2. In other words, there'll be 2.5 volts or whatever you've measured there as well. So the easiest way to do this is get your supply on the bench, find that pin 1 or whatever pin it is on the IC that you found, stick a little wire on it, turn the supply on and measure what voltage you've got there on the control pin of your IC. If that's 2.5 volts, then what you want to do is just re-engineer it to give you 2.5 volts at that pin, not when you've got 12 volts at the 12-volt output, but when you've got 13.8. Now, another little thing that you'll see here is that there's also a resistor on to the 5-volt rail. Normally, what happens with these is that the one going to the 12-volt rail is just a token gesture. The actual real meat of the regulation is done from the 5-volt rail, which is where all the current's drawn by your computer. So what we're going to do basically is get rid of that one altogether, leaving us with a very simple circuit there. And all we need to do is choose the values of R1 and R2 to give us 2.5 volts at pin 1 when you've got not 12 volts at the output, but 13.8. Hope that's clear. We'll go over it again at the end if anybody didn't catch that, but I also believe that we can put these PowerPoint slides on the Bury Radio Society website or wherever else you want to put them. They can be available at the end, so you don't have to make notes on this if you don't want. You can go back and look at these diagrams. So having done that, the easiest way to do this is the technique that I used. First of all, having figured out that it's 2.5 volts that I need at pin 1 by measuring it with the supply running as it is, take the board out and I lifted one end of R1. Now, the reason I didn't just rip out R1 is because these supplies can be finicky. And if you just lift one end of a component, you know where it went, you can easily put it back. And if you end up messing up your resistors and the supply won't start, which it won't start if things are wrong, and if you've gone wrong, it'll just refuse to come on. You can always just put them back in position and get back to a working unit while you figure out what you did. So I would just lift one end of R1 up, and having got one end isolated, you can measure its value with your multimeter, and then you can put it back. You now know the value of R1, so now, simple Ohm's law, you can work out the value of R2. If I go back, we also had R3 and R6 there. You want to lift them, don't rip them out, just lift them, disconnect them, so you can always put them back later if you need to go back. So now we're going to lift the existing R2, one end of it, and now we can calculate a new value of R2. You can use the existing resistor as part of it as you like, or you can just stick a wire on like I did, put the new R2 and a little trimmer on a piece of perf board, stick it somewhere inside the case with some silicone glue, or you can even make it so that there's a screwdriver hole so you can adjust the trimmer from the outside if you like. I had to make mine up with a couple of fixed resistors and a little small value trim pot in series just to let me finally tweak the 13.8 volts exactly where I wanted it. But that's basically the modification. It's just going to cost you a couple of resistors and a trimmer. And these don't need to be power resistors. 1/4 watt ones will do. We're only talking signal stuff here. Let's look at another one. I'll give you another example of doing exactly the same thing with a different control chip. This one's an SG6105. This one is the actual chip that's in the supply that I actually built, which I'm going to show you in a little while. Again, same logic applies. With the SG6105, you don't have an external reference for the comparator because the chip generates its own internal voltage reference. All you have here is the control components. And judging by the thing there, you can pretty much clearly see that it's pin 17. It can't be pin 16 because there's a capacitor in there, so you won't be doing any DC sensing on that. Pin 17 is the control chip, pin, helpfully labeled in, so you can see which one it is. And again, it's the same logic. We have R97 there and VR3 going down to ground. So if you lift the top end of R97, you can measure the value of R97 and that trimmer. Yes, they even actually put the trimmer in on the supply that I got. The trimmer was there, and it was even labeled VR3 on the circuit board, would you believe? So that's an indication for you that these guys really do just use the application notes when they're building these things. So we can measure that value there. So now we know what the resistor to ground is. We can ditch the one that goes to 5 volts. We can just get rid of that altogether. Calculate a new value for R94 to give us 2.5 volts there at pin 17 when the output is not 12 volts but 13.8. And then install it. Just a little note about these. Those two components connected to pin 16 there, the resistor and the capacitor, I'm not entirely sure what that does, to be honest. Somebody probably correct me on that. Someone who knows much more about these than I do. But I do know that if you disconnect them, it stops working. So if you're ever working with one of these, don't take them off. Basically, all you're doing is changing these resistor ratios. And if you leave everything else alone and don't touch it, you'll be fine. Okay, let's move on a little further. Hopefully everybody's enjoying this so far and getting something out of it. So that's basically all you have to do to convert one of these things to give you 13.8. Having got those resistors, put it back together, see if it starts up. Now, if it doesn't start up, as I've said, these supplies are finicky. If you haven't got the right voltage on that control pin, it won't start because the over voltage or the under voltage protection in the supply is going to kick in. It's going to refuse to run. What you'll probably see is the fan in the case will just give a little hint of a little attempt at a rotation and then it'll just instantly stop. That will not go away if you just switch the supply off. You've actually got to physically disconnect the mains for a few seconds and then plug the mains back in to reset that. Just check your work, check your calculation, see what it was that you did. You can always put the old resistors back the way that they were to get the supply running again while you figure out what you did wrong. Yes, I did that. That's why it's a good tip. Here's another good tip. If you're really struggling with the unit turned off, stick 13.8 volts into the 12 volt output wire from an external supply because it'll find its way back through those resistors to that pin, the control pin on your IC, and you can actually measure what your potential divider is doing there and see if you've got it right. Assuming it's all working, you've got it running with your new resistors, just tweak the little trimmer, adjust the output voltage as necessary, and then check it regulates. Because what we've done here is not just adjusted it for from 12 volts to 13.8 volts, we've actually transferred the sensing for the regulation completely to that 12 volt rail. So it should now regulate very well. Finally, don't forget to permanently connect the green wire to one of your blacks. You can chop off all the output cables except the yellow ones that you want and a matching number of black ones. Just crop the others off and use them for hookup wire. You want some sort of output terminals, a connector, an LED. And if you need extra output filtering, you could add that. You could do a bifilar winding, the yellow and blacks round and round through a ferrite toroid just inside the case. You could stick some disc ceramics across it if you're concerned about RFI and if you have any trouble with it. Now, this is the interesting point where we're going to attempt to show you the one that I've actually got here. Right, here it is. As they say on Blue Peter, here's one I prepared earlier. This is the unit. Try not to knock over my water, which would be really bad. This one claims to be high power, and it claims to be able to do 12 volts at 13 amps, which is quite good. I've loaded it up to 10 amps, and it does that okay. With PFC, wonderful thing. Here's the output. Nothing very special. It's just the wires, basically, the yellow and the black, connected to a hideous bit of chocolate block going up into my 2-meter rig, which is up there. And if I switch it on, the fan starts up and the light glows. And there's the rig there, giving me 13.5 volts. That'll creep up to 13.7 if I leave this running for a couple of minutes. And that's the that's tuned to the Berry Radio Society net frequency. Yeah. Who wants my chocolate wafers? So if you've ever worked with me on the Berry Radio Society net, you've actually listened to this power supply. There it is. It's pretty simple and it basically works. Not a lot really more to tell you about it. So we'll attempt to go back and change back over to the other system. Oh, Tristan is a worker of magic. Okay, you had a look at the one I made. That worked. More information just as we bring this to a close. It's been done before by other people, this. I don't claim any great originality for it. There is info out there, but it can be difficult to find. If you've got back issues of Radcom, July 1992, there was an article about doing this very same thing in Radcom. November 1998 and December 1998, there's a two-part article on actually building a switch mode power supply from scratch, basically, by Phil Harmon, VK6APH. And he goes into massive levels of detail about how the supply works, far more detail than I've given you tonight. I've given you basically just the information that you need to be able to hack one of these things and turn it into a supply that you can just bend to your will. You really want to get into it, you know, the rabbit hole is deep. If it helps anybody, I've got an abstract of those articles. I have some, not all, of those control IC data sheets. If anybody comes across a particular one and wants to see if I've already got it to save them inventing the wheel again, contact me through the Berry Radio Society website or however else we do it. And I'll help you out if I can. But hey, it's simple, it's easy. It's a 13.8 volt regulated supply at 10 amp for the price of 3 resistors. And I hope you found it useful. And there you go. So I will now stop sharing my screen, throw it over to Tristan and let him do his MC thing. So thanks a lot. I've enjoyed it.
Well, thank you ever so much, Alan. Absolutely fantastic. Very, very useful topic of turning a ATX power supply that would be junk into a useful power supply for amateur radio equipment. Anyway, thank you everyone for watching. Who has a question for Alan? He likes some really difficult questions, so just unmute your mic and fire away.
Alan,
Yeah.
did you check the short circuit prevention thing on there and over voltage, etc.?
I didn't find I needed to. Certainly
did you short the leads together and check?
Oh, did I test it? Yes,
yeah.
I did test it and it does work. Yeah.
Right. It's always reassuring that.
Yeah, you can't always assume that they've built these things properly. If they've been built to the ATX specification, they should have all those protections in them. But yeah, I don't trust these things.
Alan, I have a question on the power supply, those electrolytics, the big ones.
Yeah.
Do they have terminals that you can get a bleeder on or take the voltage measurement to see if they're still charged?
They do have terminals. Most of these are just your standard discrete component ones. They're not surface mount construction or anything. So if you turn the board over, you can very easily just stick a bleeder resistor across the pins, the traces that connect to those capacitors. It's easy to do. You could also measure there to check. If you're at all worried, I would just short them out with a resistor or something. In practice, the two that I've worked on here did discharge after a few minutes. They didn't hold the charge for ages and ages. But
that's because they did put the resistor in.
Yeah, probably. Yeah, but if yeah, you shouldn't really need to be messing about on the high voltage side of this. You know, all we're doing here is working on the low voltage side to convert the comparator. So again, if you can go as far as you like with these supplies, but I would say don't touch the hot side. It's not worth it.
Alan,
Yes, sir.
did you ever get any problems with RF noise at the output?
As I've said, on this particular one here that I showed you, not a whisper. It's completely quiet. And you saw there when I was waving the screen around, it's basically on the bench right next to my TS520. And I just had a wire just hooked up in the garage, just literally above it. And there's nothing. But I have another one just higher up on the bench there that is up here. You can't see it. Which I turned into a bench power supply. That one's horrible. It's atrocious. It spews all over the HF bands. So again, it depends on the filtering that's in the particular unit you choose to work with. And if you get one that's giving you trouble and you just can't fix it and get rid of the RFI by simple means, I would just get a different one. Again, these things are easy to come by. Why bang your head against it?
Well, thanks for that, Alan. The reason I ask, of course, is that I've just procured an SMP supply, and it's as noisy as anything. So what I'm doing now is, I'm contrary to your very practical advice, especially for the Yorkshireman, of throwing it all away. What I'm going to do is do a lot of research and see if I can conquer this problem. A lot of it seems to come down to resistor capacitor networks known as snubbers, which I'm going to be looking into and playing with. And I shall report back in due course. Thank you.
Yeah, just seen a message from Steve there. Yeah, please be careful. These things can bite. They can indeed, and that's why I made sure that we included the safety information there.
The other thing to be careful of is that you are carefully referring to ATX power supplies. If anyone's got a really old computer with an AT power supply, connections are different. Power supply is different.
Yeah, and the later ones are also different.
Indeed, as are PS30s and 50s.
Yeah.
Just a quick one, Alan. It's Darren, M0YDJ.
Hello.
I've got a couple of server power supplies that I've actually modified. You can get a good 60 to 70 amps out of some of them, and they seem very clean. Obviously, they're built for servers, so they've got to be, they've got to be cleaner than the 2 a penny ATX types. There are some really dodgy ATX power supplies about, really built cheaply. And the safety inside them, as you can see, probably on one of the ones that you've got there, there's open mains just on the back of the sockets and stuff that should really be screened, which aren't. So you've got to be careful when you're digging around with screwdrivers and stuff. But yeah, the server power supplies, you can get about 60, 70 amps out of some of them. And there's actually adjustments inside, so you don't have to change any components. You can just actually turn them up. I think the one I've got, the Hewlett-Packard power supply that I'm using, I've managed to get 13.2 volts out of that one, and that's been working rock solid for about 2 or 3 years. So yeah, it's worth having a look on eBay and what have you, and you can pick them up for about 15, 20 quid. So if you want a big hefty thing, 60, 70 amps, and that's the way to go. Okie doke.
Yeah, I'd agree with all of those points. Some of these are pretty nasty inside. Again, it goes back to what I said. Just assume that everything inside it is live at mains voltage. Work on it accordingly. Don't stick your fingers inside. Don't stick tools inside. If you're going to make measurements, set your measurement up with a piece of wire coming out, then turn it on without putting your fingers in, measure what you're doing, turn it off, disconnect it, and then do the next thing. It's just not worth poking around in there, because we know what it's like. You can get all excited, you can get all into the moment, and you can be in your fault finding mode, and before you know what happening, your probe slips or your finger goes where it shouldn't, and your eyes are going to light up or worse. So these things can be dangerous. I've said this repeatedly, and I'm saying it again. If you don't feel confident, don't do it. you can buy one on eBay, or you can get something else that you can do it with. But for those that are of a practical bent who think this might be interesting, I'll provide the information and just explaining what I did, basically.
Thanks, Alan. I've got a few questions on the chat.
Yeah.
Lex Papa Hotel 2 Lima Bravo says, question, when it breaks down or starts oscillating, is there any chance of high voltage on the secondary side?
You would think not. You shouldn't get that because the protection should kick in and shut it down. As I said, one of the things that you'll find about these, if they're not working properly, they shut down instantly. And that can be really, really maddening when you're trying to find out why the thing won't come on, especially when you're trying to modify it. Because if you think about it, you can't go in there and measure the voltages that it's putting out to see what you did wrong, because it won't start up to generate any voltages. So it's chicken and egg. These things can be the most frustrating things in the world to try and fault find on. Those of you on the BerryNet will know that I spent 3 weeks fixing one in a Yamaha power amp and finally conquered the thing. So yeah, you shouldn't get issues. I mean, it is oscillating all the time. It's got this power oscillator running in it, and there isn't any sort of anything else after that. It's all smoothing and rectifiers. So it's not the same as a linear regulator where you could possibly get oscillations going on, I guess, on the output. It's one of those things. It either works or it doesn't, really.
Steve M0MOI or Moi says, please be careful. I've had years of experience and these things can bite. There we are. Did you find any teeth in yours, Alan?
No, but I agree with what he says.
Yeah. Mike Golf Delta 6 India Charlie Romeo. I've had a few original 5 and 10 volt Farnell supplies. Are they modifiable? Probably 30 years old, but still working well.
Who knows? First thing you need to try and do is find some information on them. If you can get a circuit or something, or at least use the same logic, open it up and see if you can work out how the actual pulse width is being controlled. You know, if it has a chip in it that you can identify, you can use the same approach, try and find the data sheet, and the data sheet will probably give you the answers. I suspect that it probably works in a similar way to the ATX ones that we've looked at tonight. And if it does, you can probably get an in there.
Jeff Kilo 6 Tango Foxtrot Zulu says, can you parallel 2 of the yellow 18 amp wires to get twice as many amps?
That depends on the supply you've got. I have seen some of the expensive ones where they actually do have twin 12 volt outputs. Certainly the one that I've shown you here tonight, all the yellow wires just go back and they come from the same place. So the fact that it's got multiple wires doesn't mean it's got multiple 12 volt outputs. It just means that they've connected loads of wires for different things to the same one. So, I mean, I do parallel them all up, but just because it gives me a fatter wire, not because there's multiple outputs that you can run together.
Okay, and John says, great presentation, many thanks. By the way, the supply here works quietly, except for switching noise right bang in the middle of the 20-meter phone band.
Yeah, so, it's the filtering again. We've had a few questions about it. The 2 things to look at is the input and the output. Quite often what you find, as people have said, is these supplies, you know, you can get them where they've omitted all of the mains filtering components. They're just, you know, the holes are there for them on the board, and for whatever reason, to save a few quid, they just didn't bother putting them in. You know, if you get one like that, it's probably going to be horrible. You're going to need to build a decent mains input filter on it, or, you know, just as a cheap attempt, try sticking the mains lead as many times as you can, wrapping it around a ferrite core. See if it improves things. You'll know that your problem is on the input side. And again, on the output, the more smoothing you can put in. Ferrite core is your friend. You know, you could put a pi network in there. Have a look at the diagrams, you know, see the toroids and stuff that's in some of the old ones. If you get a dead one, use the components out of that, rip it apart, cannibalize it, and, you know, pinch the filter in, stick it into your other one and make it better.
I mean, another solution for John would be to forget about the phone end of the 20-meter band and learn CW. There we go. Over to you, Lawrence, for your question.
Yeah, whilst these power supplies for computers are virtually constant current, are these power supplies any use for, say, SSB PAs?
That's a good question. I haven't actually tried it because I haven't got an SSB rig here. I'm running it on FM. It should be okay because it should regulate, but quite what it does with the variable load that an SSB rig is going to present is a good question. Why don't you build one and test it and come back to us, Lawrence, and let us know whether it works okay.
Karl, KO8S, says, have you thought of adding a small LED voltmeter to your supply? 73 from Karl.
Yes, I have. If you can see it. There's my bench one. And I can't turn it on because I pulled the mains out, but there's the LED voltmeter and current meter.
Great stuff.
Did you see that, or was I just waving the PC in the air?
No, I saw that. Nobody else did.
Okay.
Right, Will, got Whiskey 6, Sugar Whiskey Foxtrot. This is a good tip, actually. Gamer power supplies usually have a cleaner output and have a lot of spit. And gamers are changing out their power supplies all the time, looking for the latest thing. I have 2 high power supplies from my son's PCs, and he's eager to try this mod. So that's Will W6SWF. Yeah, great. I mean, you get different qualities of these. The ones for gamers and the ones for high-end machines are going to be much better than your cheap junk. So yeah, I think that's a great idea. Golf Zero Papa Delta Zulu says, thanks for the great talk. I used a server type supply 13.5 volts at 40 amps. 40 amps, very good. Michael 280 IHW. I have a number of old PC PSUs, mostly unidentifiable. Can the SM transformers be used for anything else? For example, RF chokes? I don't know. You can certainly get some decent toroids out of them. Whether they're any good for megahertz, I'm not sure, but you could certainly use them for filtering. And the other thing that's well worth pulling out of these old power supplies, of course, is the big fat capacitors and the hefty diodes, the rectifiers. You can get quite a few good components out of them, even if you scrap them. Okay, Neil Ormos says, if there are multiple independent outputs, how are they regulated? They're usually not. As I said, the one that I showed you, the diagram, the lion's share of the regulation is done on the 5-volt rail, and the 12-volt rail is kind of regulated as an afterthought. You've got to choose one of the outputs and make that the regulation source that you're going to feed back to control the input. Because remember, you're regulating on the input here. It's different to a linear power supply where the regulation is done by dumping spare power at the output. You're actually feeding back to the input and regulating at the beginning. So you've got to sample one of your output voltages and use it to be the reference for that. Usually it's 5-volt rail because that's the one where the majority of the power's sucked by the computer. How they would do it for multiple ones? Well, there probably is circuits out there where they do it, but I would think on certainly most of the ones that you're going to encounter, it's going to be one rail or the other, and usually it's 5 volts, which is why you want to change it. You get one, for example, the one I've got up there on the bench, the 12-volt rail only gives me 11.6. If I load the 5-volt rail up to about 5 amps, it gives me 12.2. So it's regulating by not regulating, if you understand. Load something else, it makes it look like it's regulating. I don't know if that made sense. I know what it meant.
Yeah, they're all just moving in ratio. So you've got that 12-volt feedback into the regulation is almost a bonkers bit of design. It makes no logical sense. Yeah, and when you look at the resistor values, if you've got one like that with one off the 12-volt rail and one off the 5-volt rail, you'll wonder why did they put the 12-volt one anyway? Because it's, the resistor is 10 times the value. So it's going to have like a 1/10 of the effect. So why is it even there? So that's all I have in the chat.
does anybody else have any questions for Alan?
Just to say thank you very much, Alan. It was extremely interesting. And of course, it worked a lot better with a magic eye valve on it, wouldn't it? Yeah, it was very interesting. Thank you very much.
Yeah. Oh, good. Thanks. I hope it was useful to somebody. Obviously, I've just kept it to the basics of here's what you need to do. You can ignore all the rest. You know, if you want to modify one of these things, here's the key. Here's how I did it. So be careful though. Don't go poking your fingers in it and don't blow yourselves up.
Yeah, that's something that I would like to ask Alan. On a lot of these power supplies, there's a sticker that says something about high something pot. Do you know what that means?
I think I know what it means. I think that's the sticker that they stick on at the factory just to say that they've tested it and the output voltage is what they expect.
Right, okay. I wondered whether there was some modification that had become compulsory. Thanks for that.
Contribution?
Hi, go ahead.
High pot in North America refers to high potential, and equipment is exposed to spark-like high potential to make sure that it is safe.
Ah.
That's at the factory.
Oh, thanks very much for that, Sir John.
Oh, you're welcome. I was at Glen Eyre Electronics here in Vancouver, and high pot testing was quite normal.
Well, thank you ever so much, Alan, for a wonderful talk. And I hope the Warrington Club enjoyed it too. And it's quite amazing what you can do when, with a bit of time and a few resistors and a bit of tenacity, how you can convert a junk power supply into something of some use. So thank you, everybody, for joining us this evening. And thank you, Alan, for your talk.
Pleasure.